Good evening and welcome to the Wednesday night Facebook class from Lindsley Avenue Church of Christ. Appreciate everyone joining us here on Facebook. We're continuing our study of why I believe. And last week, we had a brief introduction to the idea of, is the Bible without error? Most Christians take it for granted that the Bible is without error. And I think in large degree, that's because coming from God, the Bible should be without error. We talked about a few things to be careful of. The Bible that we're talking about would have been the original message given to the writers in the New Testament. You always have to be aware that over time, copyist errors, either early on copy errors where people were making copies of the original documents and then copies of the copies, have led to some variant readings, and that analysis of trying to get to what the original reading was is a product of what's known as textual criticism. Not all textual criticism comes from a liberal viewpoint, liberal here meaning attempting to deny the validity or the historical reliability of the Bible. There is a need for textual criticism when you have variant readings, if you're trying to determine what the original reading was. And we talked about that last week. That poses no concerns, in my opinion, to our faith. It doesn't pose any to mine. Again, this is why I believe. But if you want to see that, go back to last week's class, which is also available here on Facebook, and you can see what I thought about it. We're transitioning a bit here with this class, looking more at if there is a God, a grand designer, a first cause, a source of all moral good, and if this designer, creator, first cause, source of all good communicated anything to humanity, and if that communication is expressed in Christianity, well, what about the competing, if you will, worldview that's not the religious worldview, that is scientism or science with a capital S? And we're going to talk for several classes about various aspects of science, as well as talking a bit about evolution in the weeks to come. By way of introduction tonight, I want to talk about the nature and limits of science, the nature and limits of science. So let's jump right on in. So what is the nature of science? What are the limits of science? Listening to some people, especially out in the media or those that you might find on the internet who appear to be scientists, and many of them are scientists, you might conclude that science really has no limits. Science, again, capital S here, we are told will not only solve all of our problems today, but it can explain anything you wish to know about the past and the future in terms of anything that really matters to questions those of us who are not scientists may actually have. Is that really how science works? What, if any, limits are there to scientific knowledge? And there are several things to consider. First of all, characteristics of science. Science refers to a set of disciplines with certain features in common. The most important common characteristic in the sciences is that there's the possibility of making precise statements that can be checked or confirmed. Basically, a hypothesis that can then be evaluated and checked with empirical data. Empiricism is an important aspect of most sciences, although some sciences that's very difficult to come by. But this idea that you can make precise statements, that you can check or confirm it, implies certain consequences. First, the subject matter repeats. Not always on a convenient time scale, but it has to repeat if it's going to be checked or confirmed. A one-time event by its very nature is difficult to view in any scientific manner because you can't check your explanation of that one-time event. And so you need to have it be repeatable. Think again of an experiment, something that you can set up and run over and over again and try different explanations, make more precise measurements. Subject matter needs really to repeat for it to be truly scientific in a broad sense. And science studies phenomena, things that occur within the natural world. I don't mean to crush any bubbles of mathematicians. I know several mathematicians are friends of mine, but math and sciences are often grouped together. But to an extent that we're talking about phenomena, math is not a science. Math is how you describe things that may be subject matter for science, but math is not a science because it's not a phenomena. Despite the fact that you can measure or estimate the area under a curve or the volume of a solid, we're not really talking about going out and observing some phenomenon trying to explain it. Science does not have to be exact. Approximations are, in fact, generally the rule. It's hard, very, very hard to be exact. And so what that means is one set of uh, explanations for subject matter that has been observed may explain it to one degree, and then years later, sometimes another set of equations or explanations is evaluated and it explains it better. Think of Isaac Newton and his laws of motion. They work, generally speaking, for most everyday thing that you and I would ever be concerned about. But then Einstein came and explained it to a much greater degree with general relativity. By the way, without general relativity and the mathematics involved in general relativity, our GPS measurements and satellite systems on our phones would be off by several miles. Imagine GPS getting you, it's in here somewhere as the answer when you're trying to go to a restaurant. Isaac Newton, because of gravitation and where the GPS satellites are located, would not be accurate enough to get us where we are going. General relativity provided that additional accuracy beyond what Newton had. Now, Newton, again, is perfectly fine for most everyday things, but we get more accurate explanations as we come up with better models. We have two branches, both of which can be precise and can be checked. Quantitative sciences make exact measurements, providing precise results. And exact here, I should have put that in quote marks because what does exact mean? But you can provide numerical, if you will, measurements that provide, again, quote marks, precise results. But then you also have descriptive sciences, and these tend to develop classification schemes. Behavioral sciences fall into this. These are not things that are easy to make quantitative or to repeat and make predictions. Let's talk about some assumptions of science. The sciences do make several assumptions. Among the most important of these, it's really something that we just assume, but it's that events in the universe are comprehensible. The universe behaves in a way that our minds can make sense of. And that's an interesting assumption. And it really means that events are not random or arbitrary. Suppose pushing something off a desk would randomly either make the object fall to the ground or do a loop-the-loop and fly off into another dimension or whatever. If that were the case, that would be very, very difficult to formulate something that would explain what happens when you push something off your desk. So this idea that events in the universe are comprehensible, it turns out is only a few hundred years old. For most of humanity's history, many viewed the world as a place governed by either the whims of God, the gods, or by chance. Note that this means direct acts of God in history may be unscientific, I do have that in quote marks, in the sense that they are unexplainable by natural means. When we talk about a miracle, in the sense of lengthening the day, if you're looking to Joshua chapter 10, or a resurrection, coming back from the dead, or healing somebody of sickness, or whatever it may be, these are not things that you and I are going to be able to put into a laboratory and see repeated. And they are not explained by any natural scientific means. So what that means is there's a lot of things that from a religious viewpoint are unscientific because they're not going to be able to be fit, as we used to say, into a test tube. Being unscientific, however, does not mean they did not occur. It does not mean necessarily that they did, but the fact that they would be unscientific is not something that means they are not possible or did not occur. So events in the universe are comprehensible. And here's another one that we tend to assume, and that is that the basic rules of science are the same throughout the universe. We have really only been able to measure a small portion of the universe being as immense as it is. It certainly appears that gravity on the surface of the Earth works in pretty much the same way as gravity does on the surface of Mars, given the difference in the Earth and the Mars's masses. But beyond that, when we look light years away and billions, trillions, quadrillions of miles out into the universe, other galaxies, it is making an assumption that these basic rules of science are the same throughout the universe. You can make observations that certainly would imply that they are, but it's an assumption because we have not been able to make, in all cases by any means, measurements in other areas of the universe that are much, much further away, say, than the surface of Mars. What is discovered, the reason this is important, is what is discovered in one part of the universe is applicable in another part. Seems pretty commonsensical, but if we discover something here in the lab, that ought to work in a lab on some planet on Andromeda, in the galaxy of Andromeda, or wherever. Something that works here should apply somewhere else. Again, we do take this for granted, but 500 years ago, this was not the case. Newton said that the universe was like a clock movement of hands, the result of the motion of hidden gears. In other words, natural phenomena, he felt, were the result of a few natural laws. Those natural laws do in fact exist because there are laws that do govern different aspects of how the universe works. They're simply a bit more complicated, to talk about Einstein again, laying out a more precise measurement than Newton's laws would have given. There's also an important aspect of it that we need to think about, and that is the scientific method. The scientific method is a procedure, it's a process by which scientists go about investigating how things work. The basic goal of science is to develop a theory or a model which provides a basis for research to understand what's being studied. The model is useful only insofar as it helps to explain the observations. Sometimes a model or a hypothesis is created and then experiments are devised to see whether the model is true. I'm afraid the likelihood here is that many times the observations are all accumulated and then a model is tried to be developed to explain all the observations, going about it the opposite direction. A model or theory does not say that A equals B, but instead says that A acts as if it were B. Now, if A were B, then it would, of course, act the same. But it simply says it sure seems like A is in fact B. It doesn't say that they are, but for practical purposes, if you see A, it's as if you see B. Science develops by a formal procedure, which is not unique to science, that includes these steps, although they're not always followed in this order. Identify the problem, gather information, propose a solution, test the solution, and then look either for other problems if that solution worked, or propose a different solution. You might get in a loop here for 3 and 4, maybe even 3, 4, and 5 if other problems help you refine your solution. Sometimes you don't necessarily follow these steps in this order, but the scientific method is explained in high school, certainly in college, and it's an important thing to keep in mind of how science works. There also are checks and balances. The sciences do have a set of checks and balances to ensure consistency and refinement. A science must make precise statements that can be checked. If a scientist proposes something that cannot be checked, it, to an extent, is as good as useless. If you make a statement that no one else can verify, then you might as well have said that a unicorn walked into the room. What this means in terms of precise statements that can be checked, we've already talked about a couple of these. One is repetition. You have to give conditions under which this phenomena can be reproduced. If you want to check some proposal I make from a scientific method, I need to describe, here's how I did it, so that you, somewhere else, without me either being present or having any involvement in it, can repeat the experiment and see what you find out. If others can reproduce the phenomena, make the phenomena appear, whether it's make particles be generated in a certain way, then they can verify the measurements. If the phenomena are not reproducible, then the statements are considered not reliable and so shouldn't be accepted as science. There's been all sorts of scandals in some of the sciences because bad science has been getting through that's not really repeatable, and that's a problem. Science should work where you have these checks and balances. Sometimes it does not. Scientists are human as well. You also have a consensus, another method really to check correctness. If different observers in different places obtain the same results, then you can have a high degree of confidence in the correctness of the results. Consensus should not mean authority, where people agree because they are the smart, really high-powered professionals, and if they say X is true, X must be true because they said it. Appeals to authority should be discarded unless you have refined measurements and repetition and consensus through experiments. Sadly, as we'll see, that has not always been the case. It's usually true in terms of repetition and consensus, but not always, because it is possible everybody can make the same mistake. Certainly, if I have not described the situation under which I have made my measurements and generated my phenomena, then you might fall down the same wrong alley that I did. And mass hysteria could be present. Sometimes people are so excited about getting to a final conclusion to something that people just are blind to the faults in the experiment or in the process. A consequence of the requirements of reproducibility and consensus is there is no place for unquestioning acceptance of authority in science. There is a need to accept things that are demonstrated and repeatable, and if you reject it because you don't know what people are talking about, that's not a good reason to reject anything. But if you see statements of authority and statements that there's no reason to ever question this again, remember Isaac Newton. Isaac Newton had things that if we had not continued to question, if we had not continued to make observations and had not continued to make measurements, our GPSs would not work. So when I see personally appeals to authority or criticism of questions, that causes me some heartburn, as we would say. No report should be considered acceptable unless it is presented so that it can be duplicated by, here's the key thing here too, independent observers. An example of this might be the cold fusion confusion. I guess it was now in the late 1980s or early 1990s. A couple of scientists indicated that they were able to have fusion occur at room temperature with some palladium and some other things, and that this would have been a revolution if this were the case. We're still trying to get hot fusion to work. Imagine if you could have a little thing on your desk over here that at room temperature generated more energy than you put in. It would have been truly revolutionary. Problem is, it has not been easy at all to repeat and have a consensus of others who have seen the same results. There are still some people chasing after this, but I certainly would not in any way think that that is an accepted explanation of reality in terms of cold fusion. Might be in years from now, but as of right now, there's been a lot of confusion because things were not specified to the degree required to have other people be able to repeat it. And when people have tried, they have not been able to repeat it consistently. Another aspect about the nature and limits of science we need to keep in mind is something related to this idea of the uncertainty principle. Werner Heisenberg formulated the uncertainty principle. Life in the world, in the universe, is subject to this uncertainty principle. Basically, it states that measurement or observation influences the object being observed or measured. Suppose it's this way. Suppose you have somebody who works in an office and unobserved, you think that perhaps they're sleeping at their desk or doing something like that. Well, if you put in a glass window behind them, and they can see you staring out at them, do you not think that if they had been sleeping, they're going to be influenced by the fact that somebody's looking out a window staring at them? Of course, they may turn out to be the most productive worker the world's ever seen. Observation has influenced the object being observed or measured, and so you're not getting a measurement of reality. You've influenced reality by the process of measurement. This means that there's a limit to what can be known with certainty about objects, especially those that are very, very small. It actually isn't as applied all that much to people in offices. The Hawthorne effect, you can Google that. That is applied many times to people in offices. But when you think about the subatomic level or things like that, it really is important because there's a limit to what you can know with certainty, which means what? Suppose you wanted to measure the position of an electron. You have an atom, protons, maybe some neutrons, an electron or electrons going around the atom. You wanted to measure the position of an electron. Where is it at this instant? One way you might do this is to shine a light, actually a stream of photons, at the atom trying to ping, if you will, or bounce off an electron as it orbited an atom, and you're looking for the scattering of light. Think of it as a reflection. Think of billiard balls. That's not what they are, but think of a billiard ball being thrown into an atom. If it hits an electron, it's going to bounce, and by the bounce, you can try to figure out, here's where it was. Well, to an extent, right? Imagine that's how it's going to work. The problem arises is that at the level of the size of an electron, which is incredibly small, The photons in the light source might bounce off an electron so you could see where it was, but in doing this, you affect the speed and direction of the electron. This would mean that you could determine where it was, right, when it bounced off, but you could not any longer tell where it was going. So if you were trying to make a model of here's where it is, okay, so it's going around, no. Once you determine where it is, you can't tell how fast it's going, its direction of travel, any of that. You have influenced what you were measuring by the process of measuring. So it affected, in this case, the electron. Similarly, if you wanted to know where it was going, you could determine that, but you could no longer tell its exact location. You could know one of these two properties, but not both of them. So its effects and consequences underlies much of what modern physics has to deal with. In fact, this principle has a lot to say about the certainty with which we can know anything to an extent for sure about the world. What we can say is that we possess a level of confidence in our knowledge about how the world works. Again, I don't get in a car and worry that, well, how's this car going to work? We understand things well enough that we know how cars work. We know how computers work. I mean, we got a great deal of certainty about a lot of things that would have been very, very hard to imagine 100 years ago, several hundred years ago. But theories and explanations offered by science are always in a state of change. Will general relativity be replaced by something even more fantastical and precise? Perhaps. Physicists have been chasing a theory of everything, whether string theory or different aspects of gravity, for a long time. Science, the explanations, the theories are always in a state of change, which again goes back to when somebody tells you that the science is settled or there's no need to question things anymore. Science progresses by questioning things. And so sciences usually are in the process of chasing more accuracy, greater certainty. And so it's always in a state of change. Theories work only insofar as they make accurate predictions about a future situation. And this leads to the next thing to consider. What is our level of certainty about scientific knowledge? Some areas of science lead to higher levels of certainty in what they propose to be true than other areas of science. Let me give you some examples. Consider the differences proposed by physics, paleontology, and astronomy. Physics. Physics is a very quantitative science. Scientists studying physics can propose theories and test them. It's gotten much more mathematical and, to an extent, much less empirical in testing, especially when scientists have been trying to get toward this theory of everything. String theory exists as mathematics. It's been very, very difficult to figure out ways of testing a lot of these things. But generally speaking, work equals force times distance. Think of different laws that are out there in the realm of physics. A theory might be put forth to explain why an object remains at rest or why it remains moving in a straight line until an outside force acts upon it to start it moving, stop it moving, or cause it to move in a different direction. You can put a theory like that out there and test it. It's very quantitative. So when physics tells us things about some aspects of the world, it's incredibly certain, incredibly certain. Once this theory is formed, you do these experiments and you test if the theory accurately reflects observations. The degree to which it describes what is observed corresponds to the confidence level you can have that a theory is, and I'll put this in quote marks, correct. In physics, the key idea is that a new theory can be proposed and tested by repeatable experiments. So you have a fairly high level of confidence in the accuracy of the theories if you can demonstrate by observation and experimentation that, yes, this is predicting what I need to see. Astronomy. How about astronomy? Scientists study the universe by astronomy are in an interesting position. When they look into the night sky, they are seeing things as they happened in the past. Given that light travels at a finite but incredibly fast speed, when scientists look up at the moon, it's how things were about a second and a half ago. Light that you see from moonlight on that romantic evening is actually light that bounced off the moon about a second and a half ago. The sun, we just had an eclipse. The light coming from the sun takes about 8.5 minutes once it leaves the sun's surface to get to the earth. And so let's hope it doesn't, but if the sun disappeared, you wouldn't see it in terms of no light coming anymore for another 8.5 minutes. Or if the sun went nova or something like that, you would have 8.5 minutes of blissful ignorance before you were to notice such a fact. Scientists look into the past. When they are looking at the nearest star over at Alpha Centauri, actually it's Proxima Centauri, light they see from those stars left a little over 4 years ago. When they look at the Andromeda galaxy, which you can see on a clear night, dark night, you can find the fuzzy little patch. Light that left it has, according to the speed of light, been traveling for nearly 2 million years to get here. They are looking into the past. So what does that mean? As I say, they're looking at the light that left a long time ago. So when you look at the sun, it's light that left in the past. So when scientists look into the sky, they are seeing the past unfold live right before their eyes. So if they propose a theory and look, they can watch, and they might be able to actually see an event happen that's as if it's an experiment, and see if what happened in this proposal when they identify a star that should do this, if this happened to it, measurements can be made to see what happened in the past. They are seeing the past live, right? So they make predictions in some cases and watch events unfold. In this way, knowledge gained by astronomy about the universe's past and present is in many ways much more certain than that gained by paleontology, which we'll describe next. Paleontology. Scientists studying fossils in many ways have a much tougher time than physicists or astronomers. This is because paleontology is basically a descriptive science. A theory can be proposed about how a fossil came to be or how it came to be different from another fossil, but it's really impossible to directly test this theory by performing repeatable experiments. You might be able to propose this fossil should be in this level of rock formations over in another place. Sure, you can do that kind of thing, but you're not going to be able to set that up in a lab. So it's basically a descriptive science that tells you some basic things about the past, but it's very difficult to have repeatable experiments. What they have to do is to generalize from many different observations to form a theory explaining something. In this case, theories about the past will not make precise predictions that can be tested or evaluated. Paleontology suffers from that problem. It can make general predictions about where might tend to find similar fossils, but it's difficult to be certain that only this theory would explain why the fossils were grouped the way they were. Also, another one here, climate science. Climate science, particularly as it is applied to climate change, global warming, etc., does face several challenges. It too deals with the past, and reconstructing the past like is needed for climate science is often painfully difficult. What was the average temperature near Omaha, Nebraska in July of 1872? You don't have a tremendous amount of past data. The data that you have is subject to human error in gathering it. It's subject to differences in the precision of measurement. Trying to get the past and make predictions about the future from a climate science standpoint is rather difficult compared to some of these other sciences that we've been discussing. It's also nearly impossible to find repeatable experiments. Climate scientists, therefore, have turned to using models to make predictions of future changes by making those models fit to reconstruction of past events and then extending them out into the future. In simplistic ways, businesses and college students may be familiar with the idea of regression, taking past data, fitting a curve to it, and then extending that curve out into the future. Multiple regression takes a lot of different data points and different measurements of different aspects of it, feeds it into a big computer model, and again, tries to spit out the future. So climate scientists have turned to these models, feeding in all sorts of things, and then trying to extrapolate out into the future. When predictions are not accurate, and many of them have not been, yes, it does appear that temperatures have continued to go up to an extent, but not to the extent that models were predicting, as far as I'm aware, 10, 15, 20, 30 years ago. So if they were predicting a path like this and it came in like this, why did it not turn out up here? Why is it down here? What went wrong? Well, was the input data improperly adjusted? Did the model have a mathematical mistake? Did nature simply vary? Was there a data element that needed to be in the model that was not in the model that would have predicted the path that actually resulted? Who knows? So it's a terribly difficult area of trying to generate information that can be useful about the future. Sometimes science isn't as settled as some would claim. So I will tell you right here, I think some sciences are much more settled, much more likely to give information, predictions that can be trusted and are repeatable and that are accurate than others. It's the nature of the beast, and it depends on what is being studied. How much information do I have about the past? How much am I relying upon repeatable experiments? When you get into modeling, having done financial models, many times, for some reason, my predictions of stock prices don't often turn out to be what they are a week from now. Otherwise, I'd probably be a lot richer than I really am. Summary. So generally speaking, the real difference being discussed here is that some sciences primarily deal with the past, others with the present. Knowledge about the past cannot be as certain in many ways as knowledge about the present. A paleontologist, as I said, cannot perform an experiment in the same way that a physicist can about certain aspects of physics. Cannot be done. And so I will argue that a paleontologist is certainly more limited about what they can say about the past than perhaps a physicist or an astronomer who's looking at the past visually and seeing the past unfold live with things that are occurring way out there. What is being studied in the past is fixed. You have potential additional future observations that are possible, but you cannot repeat it. Until we get a time machine and can go back and into the past and watch something actually occur, the past is at best still somewhat uncertain. Greater levels of certainty, dealing with some sciences than others. Many of the apparent conflicts, I am of the opinion, that exist between science and religion are based on interpretations of past events. I think that's the reason this is important to think about. An awareness of the limitations of science in general, and specifically of sciences dealing with the past, I believe is necessary for an understanding of what science can truly know for certain, or what it can essentially only propose. In the same way that many of us, from a religious viewpoint, need to have a bit of humility about what we would like to tell people is known for certain, then we need to have science also have a bit of humility sometimes when dealing with the past. There are certainly many things of which we are very, very confident from a religious viewpoint and from a science's viewpoint. Humility is something that often gets lost when we start having disagreements, certainly between science and religion. I want to thank you for being with us here at Lindsley Avenue this week. Please come down and see us. We'd love to have you in person. The in-person class for Wednesday night that this is replacing is discussing and having a good time going through Proverbs. Proverbs is being broadcast on Facebook as the Sunday morning class, providing this for those who may find it of value as an alternative on Facebook on Wednesday evenings. Thank you for joining us. See you next week.